and final lecture by Bernd.
Okay, so in this third lecture, it's not going to be so convex. It's going to be a problem that's coming from algebraic statistics. We're going to approximate matrices by low-rank matrices, and unlike in the morning lectures, in the morning we heard about very large matrices, so this will be about very, very small matrices. There are two papers. There's a joint paper with Hauenstein and Jose Rodriguez, and then there was a second subsequent paper by Jose and Jan Dreismer. So I'm going to look at two random variables that are discrete, that take finitely many states. The first random variable takes m states, and the second random variable takes n states. So a joint distribution assigns a probability to pairs of states. So Pij represents the probability that the first variable is in state I and the second variable is in state j. So I can organize this as an m by n matrix P whose entries are non-negative and sum to 1. So these distributions form a simplex, right? So matrices non-negative whose entries sum to 1 form a simplex of dimension mn minus 1. I'm going to write Mr for the manifold, smooth manifold of matrices of exactly rank R inside the simplex. Now M1 represents independent distributions. So two random variables are independent if Pij is the product of a quantity depending on I and a quantity depending on j. So the probability of the first variable being in state I and the second variable being in state j is the product of the first variable being in state I times the probability of the second variable being in state j. And that says this matrix is the product of a column vector and a row vector. So that's a rank 1 matrix. Mr, I'm going to call that a model. So in statistics, a statistical model is a family of probability distributions. So in this case, just a subset of this simplex. So Mr is the model for mixtures of R independent distributions or also conditionally independent distributions. So it's been a long day, so I'm going to motivate this by a light-hearted example. So I learned this from an introductory text in statistics. Of course, the UK is a sort of a hot spot for statistics, so this was a British text. I just changed the numbers a little bit. So 296 British subjects between age 40 and 50 were interviewed about the hair length and how many hours per week they watch soccer, football on television. So in blue, we have the question, right? So does watching soccer cause you to lose hair, right? Every day in the newspaper, you read that some food or some behavior causes some medical condition. The first question, is there a correlation? And then very quickly, we like to jump from correlation to causation, right? So the question we can ask. So the data were summarized here in a 3-by-3 table. So I take my two random variables. So there's a random variable soccer. So this is how many hours per week you watch soccer. So a little bit is less than 2 hours, medium between 2 and 6 hours per week, and then the true fanatics, watch more than 6 hours per week on television, soccer. And then the second random variable is hair. Again, 3 states, full hair, medium hair, and then, very little hair, right? So is there a correlation based on these data? Well, you look at the matrix, right? So independence, perfect independence would mean that the matrix is rank 1, that the 2-by-2 subdeterminants vanish. Now, if you look at these, the 2-by-2 subdeterminants, they're all positive. In this example, they're all strictly positive. In fact, by quite a margin, right? So all 2-by-2 minors are positive, and that seems to suggest that there is a positive correlation, right? So between having little hair and watching a lot of soccer, right? So is this actually the case, right? So to do this properly, you have to set up some hypothesis test and so on. But here, let's jump to the conclusion. So not really, right? Because, in fact, there is a hidden, mysterious, latent random variable or hidden random variable called gender. So gender is a random variable that has two states, male or female. And if we knew the hidden data, so if we knew that this table is the sum of a male table for 126 males and the female table for 170 females, that would perfectly explain what's going on. So in this example, the male table is exactly rank 1. The female table is exactly rank 1. Well, their sum is rank 2, right? The sum of, if you have two rank 1 matrices, you add them up, you get a rank 2 matrix. So the conclusion is that we don't have independence, but we have conditional independence. So watching soccer and hair growth are independent given gender. So for the males, it's perfectly independent. For the females, it's perfectly independent. Of course, a true statistician, so statisticians are fussy people, right? They never accept a null hypothesis. They either reject the null hypothesis or they don't, right? So you formulate this null hypothesis and you very much not reject it. Okay, this was just to illustrate the low rank discussion. So M and N in this example are 3 and R is 2. So in general, we're drawing IID, identically and independently distributed samples from an unknown joint distribution. So we don't know the probabilities Pij. The unknown real numbers, non-negative, that sum to 1. The data is a matrix U with non-negative integer entries, and I'm going to write U++ for the sample size. That's the total sum of the entries in this matrix. So U++ is the number of people in the study. And Uij is the number of people with soccer status I and hair status J. The likelihood function is the corresponding monomial in the P's. So L sub U is the monomial with this exponent matrix. So the product of the unknown Pij's raised to the power Uij. Well, if the samples are independent, this is the likelihood or probability of seeing this particular table given the sample size. It's not quite true. There's actually a multinomial. There's a normalizing constant. So ignoring the multinomial constant, we're asking the following question. Let's look at all possible tables of non-negative entries that sum to 296, that sum to U++. Each table has a very low probability, but that is the probability of seeing that table among all tables with a fixed sample size. Okay? And the goal is to maximize this function. So we have to solve this non-convex constrained optimization problem. So over all tables of rank R, we like to maximize this likelihood function, this monomial. Maximize a monomial over the model, in this case, low-rank matrices. So, okay, so we would like to, given the data, find the distribution that best explains the data. That's the goal. Now I should maybe say a word about sort of classical statistics. So long time ago, there were two different camps in statistics. There were frequentists and Bayesians. Okay? This is a frequentist question. Classical frequentist statistic question is to maximize the likelihood function. In Bayesian statistics, we do something different. We also take the likelihood function, but we integrate it against the measure on the model. So in Bayesian statistics, we have a probability measure on the manifold M called the prior distribution or prior knowledge, and we want to integrate this function against the measure. So from a mathematics point of view, from a American calculus point of view, the two flavors of calculus, differential calculus and integral calculus, manifest themselves in the two flavors of statistics, right? So frequentist statistics, we want to optimize, maximize the likelihood function. That's differential calculus. In Bayesian statistics, we want to integrate. That's integral calculus. So today, I'm going to talk about the optimization problem. But of course, algebraic methods are equally useful for the Bayesian problem of integrating this function. In fact, even deeper in some sense. Moreover, I'm going to focus here today on discrete random variables rather than Gaussians or continuous distributions. But again, the same kind of question makes sense for Gaussian models, and there's also similar algebraic approaches. So I'm going to focus on this problem. I'm going to write p hat for the solution. That's a rank R matrix. Typically, that's called the maximum likelihood estimate for U. So I'm going to be interested in the question, how does p hat depend on the data? So p hat is a function on the data. In fact, that's true for any optimization problem. Right? For any optimization problem, the optimal solution is going to be a function of the data of the instance. You want to understand the nature of that function. Let me give you the rank 1 case. The rank 1 case is very, very simple. When R is 1, so we teach this to freshman biologists at Berkeley. Okay? And here's how it goes. Okay? So you're given the data, and you want to find the best rank 1 matrix in this sense. What you do is you form the column vector of row sums. So U2 plus is the sum of the entries of the data in the second row. So this is the number of people that watch a little bit of soccer irrespective of hair length. That's a column vector. Here you have a row vector. Those are the column sums. So this counts the number of people according to their hair length irrespective of how much soccer they watch. We take the product of those two. That's a rank 1 matrix. And then we have to scale it so that the entries sum to 1 by the square of the sample size. And that is the optimal solution. Okay. In fact, this p hat, this product of column sums and row sums, is the only critical point of the likelihood function on M1, on the Segre variety, and it's the unique local and global maximum. Okay? It's a very, very simple solution. While I have the stage, let me make a few opinionated and sufficiently polemic remarks. Most people would refer to this as a simple analytic solution. In fact, you often speak to applied people, and they often use the phrase analytic solution. That adjective suggests that this solution involves the mathematical discipline analysis, and that discipline is a very useful discipline. I don't object to that, but this particular instance is not one of analysis. It's an object of analysis, of algebra. This is an algebraic solution because algebra is, in fact, very, very useful. Okay. So please try not to use the term from now on analytic solution. Please use the term algebraic solution. And if you ever use the term analytic solution again, do it very, very mindfully. So the maximum likelihood estimate in this case is a rational function of the data, right? Each entry is the ratio of two polynomials. And a rational function is an algebraic function of degree 1. So to write down, we can write down the optimal solution in the same field as the data. If we start with the field of rational numbers, we write down, just like in linear programming or in two-person Nash games, we can write down the optimal solution over the same field as the input. So that means the algebraic degree is 1. And again, non-experts, please interrupt me with questions. Okay? So this is the solution for R equals 1, and we teach this to freshmen. Let's talk about the soccer case. So the first interesting case is 3 by 3 matrices of rank 2. So here is the instance again of our optimization problem. So we're given positive integers, the u's, then the p's are the decision variables. We want to maximize this monomial subject to two constraints. One constraint is the rank drops, so the determinant vanishes, and then the entries sum to 1. Of course, in the application, we would like these p's to be non-negative real numbers. But to make the problem easier, let's disregard that for the moment. Now, not knowing anything, what you would do, you would form the critical equations. That is to say, you write down the Lagrange multiplier formulation for this problem. And here's one way to write it. So here's the constraints again. The determinant is 0. The sum of the entries is 1. And the Lagrange multiplier equations can be written like this. We form this 3×9 matrix, and require that the rows are linearly dependent. So the first row is the vectorization of the data. So these are just the constants. So these are the number of people in our data table. The second row is our unknowns, P11 up to P33. And the third row has cubic polynomials. Namely, the entry is a Pij times the corresponding cofactor. So the derivative of the determinant is the cubic polynomial with respect to any variable is a quadric. That's a cofactor in the matrix. So we take any matrix entry times the corresponding complementary cofactor, corresponding 2×2 matrix. And this is the condition. So if you think it through, that's the condition. These rows have to be linearly dependent. So of course, it's a little silly in this audience, to explain what Lagrange multipliers are, but I'm going to do it anyways. Yeah? So we have a constrained optimization problem. We have the gradient of the objective function, and it's supposed to be perpendicular to the tangent space. Okay? So I'm writing the condition. The gradient of the objective function is perpendicular to the tangent space. So you take these equations, you type them into your favorite computer algebra system. You're very careful to avoid denominators and so on. It turns out that these equations have 10 complex solutions. So the algebraic degree of this problem is 10. So for any random choice of the u's, there will be 10 complex critical points. And then some of them are real, some of them are not real, some of them are positive, some of them are not. And then among the positive real ones, we pick the one we like best. That's the maximum likelihood solution. So in this case, the function from the data to the optimal solution is an algebraic function of degree 10. So that degree, before we get there, well, we saw this actually this morning. I'm going to sort of rephrase this a little bit more in algebra language. So we're going to be interested in critical points of the likelihood function on matrices of rank R in the simplex. As always, it's easier to close and look at the complex variety, VR, of matrices of rank at most R. So we form the Zariski closure of our manifold inside complex projective space. Emmanuel this morning had the formula for the codimension. So here it is again. The codimension is m minus r times n minus r. Right? So that's the degrees of freedom in making a rank R matrix. Is that clear? So you have an m by n matrix, and you want to make a rank R matrix. You can pick the first R rows. You can pick the first R columns. And there's an overlap, right? So the shaded area is the dimension, and the unshaded area is that codimension. Now, the second question, if an algebraic variety walks into the door, the first two questions you should ask him or her are the following. First, what's your dimension? How many degrees of freedom do you have? Second question, what's your degree? How curvy are you? Right? So the degree of a variety is the number of intersection points with a complementary linear space, and that's the second question. And it's a good thing to think about this for determinantal varieties. Right? So give you some numbers. So for example, if we look at 4×5 matrices, so there are 3 cases. So there are matrices of rank 1. So that's a projective variety of dimension 7 in the 19-dimensional projective space. So this is a simplification of the 19-dimensional simplex, right? So same thing, it has dimension 7. Rank 2 matrices have dimension 13. Rank 3 matrices have dimension 17. And rank 4 matrices, that's everything. And these are their degrees. The degrees of these varieties are 35, 50, and 10. If you talk to geometers back at your home institutions, they call these things secant variety of Segre varieties. Okay, So these are determinantal varieties. We want to maximize a monomial over a determinantal variety. That's our problem.
Trivial question, back to formulas. How do you connect these numbers, 7 plus 5 to 19?
How do I connect them?
I mean, you're seeing that in 7-dimensional space, the degree is 35. Why is it projected space of 19?
Oh, why is it 19? Okay, because there are 20 matrix entries. So 4 times 5 is 20. But the simplex has dimension 19. So I talking about the 19-dimensional simplex of all joint probability distributions. And to make the problem a little easier, I work in the complex projective space of dimension 19. Why is it 7? Well, I mean, okay, so if R is 1 and M and N are 4 and 5, then the shaded area is 8. But because we're thinking projectively, it's 7. And then why is it 35? Well, if you cut this with the linear space of complementary dimension, you'll meet 35 points. That's the usual notion of degree. That tells us how curvy this thing is, right? If this were 1, it would be flat linear space. Okay? Okay, here's the ML degree. So the ML degree, the maximum likelihood degree of a statistical model or a projective variety, is the number of critical points of the likelihood function for generic data. Now there's something crazy in this sentence, namely how can the speaker be so bold to equate statistical models and projective variety? Let me explain that. If we have discrete data, such as in these cases, most or many of the models that people actually use in applications, phylogenetic models. We're hearing a talk about phylogenetic models, I believe, on Friday or Thursday. Hidden Markov models, graphical models, directed, undirected. Many of the models for discrete random variables that people actually use in bioinformatics and other applications either have a polynomial parametrization, representation, or can be reparametrized to have such a representation. I'm not saying that all statistical models are given by polynomials. I'm saying many of the models that people actually use have such a representation, and therefore it makes sense to regard statistical models in this context as projective varieties. And so we're going to be interested in the number of critical points of a monomial with random exponents. So this theorem summarizes the known values of the ML degree of our rank varieties, VR. So here are the matrix sizes, 3 by 3, 3 by 4, up to 5 by 5. So these are fairly small, okay? And here are the possible ranks, 1, 2, 3, 4, 5. Okay? Now you notice the first row consists entirely of ones, right? That was the analytic, algebraic solution for rank 1 matrices, the one we teach to freshman biologists, right? That's row sums times column sums. Likewise, here the last strip is all ones. Well, if you're looking for the best 4 by 5 matrix of rank 4, well, you just give the same matrix back, or you just divide by the sample size. That's certainly a rational function. So we also have a 1 down there. This 10 was the soccer number we saw. So 3 by 3 matrices of rank 2, the ML degree is 10. Now, this subject was first sort of studied systematically in 2004. And at that time, we looked at this. We did some calculations with the computer algebra system singular. And the only numbers we could compute were these numbers, 10 and 26. All the boldface numbers are new. They were found last year. So that's pretty lame, right? Why couldn't we go further than that? Well, the reason is that these equations involve denominators. You need to clear denominators. And that is a difficult thing. When you are doing a Grobner basis computation and you have sort of denominators to clear, this involves saturation, and these are hard calculations. So we were at that time not able to go further with singular. So I'll tell you how these numbers were found. So now there are more numbers, right? So for example, for 4 by 5 matrices, the ML degrees are 1, 843, 843, 1, right? So compare that. So the degrees were 30, 35, 50, 10. The ML degrees are 1, 8, 43, 843. Now when you look at this table, what's the first thing you notice? That's meant to be an easy question for a non-expert. So when you look at this table, the lady here on the right, what do you notice? What strikes you when you look at this table? Anything that looks kind of noteworthy, sir?
Same 191 and 199.
Yeah, right. When you go down the columns, right? So can you see from here? I'm getting a little blind, but if you go down the columns, there's a symmetry, right? It looks like there's a symmetry, right? So we see 843 twice, right? So now that was a big surprise to us, right? Because we knew these numbers, then we got that number. You know, when we come to that column, we were surprised. There was no reason that we were aware of that the two numbers should be the same, right? So we were kind of surprised to see the same number twice. Okay, we'll get to that. What else? Well, suppose you don't care at all about statistics, optimization, likelihood, soccer, none of that. But suppose you care about topology only. Okay? Well, it turns out that these are actually meaningful numbers from a topological point of view. So it turns out, that's by work of Junhe, that these numbers can be thought of as a topological invariant of the following space. I take my complex variety and I remove these mn plus 1 hyperplanes. So I'm looking at complex matrices whose entries are non-zero and the sum of whose entries are non-zero. That's an open variety. And I can look at the topological Euler characteristic of that open variety. Now, if that variety were smooth, then these numbers would be the Euler characteristic on the nose. Now, these varieties are not smooth, right? Because matrices of rank at most r are singular along matrices of rank at most r minus 1, right? So that's a fact of life. But so this notion of Euler characteristic has been to be changed a little bit, involves something called the Chern-Schwarz-McPherson class. But as I said, if you only care about the topology of these spaces, then these numbers are meaningful. And that's not so surprising, certainly to Benjamin, because Morse theory relates optimization and topology. Question? Yes, if the thing is smooth. If the U's are generic and if this were smooth and the U's were random, it would be a perfect Morse function. Okay, so that's the notion of ML degree. And we're going to get to the symmetry in a moment. Let me talk a little bit about the formulation of this optimization problem. So here's sort of a recap of Lagrange multipliers in the geometric formulation. So at a regular point, right, so an m by n matrix is a regular point inside matrices of rank at most r if the rank is exactly r. Right? Those are the regular points. We have the tangent space. The tangent space is a subspace of the shaded dimension. So the shaded number is the dimension of the tangent space, and then the unshaded area is the dimension of the orthogonal complement. Now we're going to look at the likelihood function. Actually, we're going to look at the log likelihood function, right? Because we have this monomial with large exponents. It's more convenient to look at the logarithm. So we look at, p11 times log, u11 times log p11 plus u12 times log p12 and so on. And then we can look at the partial derivatives of this. So regard this as a function on projective space, and then the partial derivative is uij divided by pij minus u plus plus the sample size, and then p plus plus. So this is the homogenizing variable in this projective space. So this is 1 in the statistical application, but this is the coordinate of the hyperplane at infinity. Okay, so the proposition is what I demonstrated with my cable 12 minutes ago. So a matrix, a regular point, is critical on this constrained optimization problem if and only if the gradient matrix is in the orthogonal complement of the tangent space. So that's the system of equation we need to solve. Okay? Well, this looks nice. But of course, if all of you know, everything is in the formulation, right? If you take the first and beautiful formulation, it never works in practice, right? You have to take the first formulation, play with it, change it, and make it really ugly. And at the end, you have a formulation that actually works. So in our case, here's the formulation that actually works. So what you do, you impose the low rank constraint in a parametric form. So you introduce unknown matrices, P1, R1, L1, lambda of the appropriate sizes. You multiply this out. These are unit matrices. Then this parameterizes the low rank matrices. And then we formulate the following system of equations in red. So this is going to be a system of mn equations and mn unknowns. It's a matrix equation. So you take P, this matrix, Hadamard product. That's the entry-wise product of two matrices. Okay, I have two matrices of the same size. The Hadamard product is the entry-wise product. I multiply entry by entry. Then I take this matrix that has the same size. Then this is a scalar, again this matrix, and that's equal to that, right? So that's a system of mn equations in mn unknowns, and the proposition says that there are finitely many complex solutions, and they exactly represent the critical points that we want. So it turns out that this square system formulation is the one that works best in our calculations. There's a similar story for symmetric matrices. So for symmetric n by n matrices, so for the correct model, you need to multiply the entries by 2, the diagonal entries of 2. So these are mixtures of identically distributed random variables. Suppose you have two random variables that are identically distributed. I don't know. Then, yeah, this is the genetics situation. So the Hardy-Weinberg equilibrium corresponds to this, the one we teach to the biologists. So then we can ask the same question. We can look at the ML degree of rank R symmetric matrices. And now for 3 by 3 matrices, we have 1, 6, 1. So 3 by 3 symmetric matrices of rank 2, ML degree 6. And we see the symmetry along the columns again. Okay? This value we didn't get yet. We were not able to get. What do you mean by factor?
The composition that you give.
Yeah, there's a similar. So in this formulation, there is a symmetric version of this. Yeah, there's a symmetric. So I'm just giving you, I give you entries. I'm giving you U11. I'm just giving you the upper triangular entries, and I want to solve the monomial, maximize the monomial in this case. And again, you notice that there's a symmetry along the columns. So before, yes, Marcus?
But your, I mean, these distributions are not non-negative functions, right? So
The P's?
the distributions of your random variables are not non-negative functions.
No, when
they are not random variables.
No, the P's, so when I talk about distribution, they're actually non-negative and in sum to 1. Okay? But I'm relaxing the problem, so instead, I'm looking for critical points among all complex solutions. So for example, so if you give me a particular table, maybe there are 270 complex critical points. Of those 200 complex critical points, 100 are real. And I don't care about the other ones. Among those, in the application, among those 100, maybe 36 are positive. I don't care about the other ones. The ones I'm most interested in are those that happen to be positive.
Maybe there is none.
Under some very mild hypotheses, there will always be one by compactness. So it turns out that in the simplex, so you look at this variety inside the simplex, and then this function will attain a critical point in the simplex. It drops off to 0 at the boundary, is positive in the interior by, I don't know, it's called the intermediate value theorem. There will be a critical point inside the simplex. Again, that can fail in the sum, but usually that's the case. Okay? Okay, so before I get to this duality in the columns, let me do one more thing. So I I earlier showed you this colorful picture and I talked about solutions and radicals. Let me talk once more about solution and radicals. Okay? Here's a concrete instance. So let's look at 3 by 3 symmetric matrices, and I'm going to pick a particular data set. Okay? So this U11 is 10, 9, 1, 21, 3, 7. Okay? So let's pretend these are my data. Okay? So there are 6 complex critical points. So in this example, Marcus, all complex critical points happen to be real and positive. Okay, so I chose the data to have this property. Okay, so and here they are. So they are the rows. Okay, so these are positive real numbers that sum to 1 in each row. Now these are the likelihood values. Okay, so it's been a long day. The logarithm of a number between 0 and 1 is a negative number. And to maximize a negative number, you have to minimize the absolute value. Okay, so that's why this is the winner. Is the largest likelihood is minus 82. Okay? So in this example, the first 3 points are local maxima, and the last 3 points are local minima. There are no saddle points. In this example, there are no saddle points. 3 local maxima, 3 local minima. Okay? And now what is the nature of these numbers? Okay, so they look like floating point numbers, and, well, the degree is 6, right? So these are algebraic numbers of degree 6 over the rationals. So can they be written in radicals? Can I write these numbers in radicals, right? I mean, this, people think they understand this, right? This is some floating point number, but can I write this in radicals? Emil, what do you think? Do you think I can write these in radicals? No, right? Because, why? Well, because it's a degree 6, right? So if I eliminate all but 1, there's one equation in one variable of degree 6. And we learn in algebra, undergraduate algebra, that by Galois theory, there's no general formula in degree 6. Except in this example, you can. Okay. So in this case, the Galois group is not X6. It's not the symmetric group on 6 letters. It's, in fact, the symmetric group on 4 letters, S4. S4 is a solvable group. So if you have an equation with a solvable group, then the equation is solvable in radicals. In this case, it is solvable in radicals. Amazing, right? So let's do it, right? So the minimal polynomial for the last coordinate, so if I look at the lower right entry of my matrix, P33, I eliminate all the other things, I get one equation of degree 6 in this P33, and then we solve it. Okay, so P33 is this thing, right? So where zeta is the primitive third root of unity, so zeta squared plus zeta plus 1 is 0. Omega 1 is the square root of this rational number. Omega 2 is the cube root of this thing, and then omega 3 is the square root of that thing. Okay? So this is the exact solution in radicals, and you can write down the other entries as well. Okay? Now what do we learn from that? Well, first of all, we get reminded that even if you write down real numbers in its exact representation, you might have to sneak in some complex numbers along the way, right? That's Cardano, that happens, right? You might have to write down some of those. But moreover, so this is an exact representation. This is the simple, easy, exact representation. Unlike this representation, which is much, much, much more complicated because you only see a few digits and you die before you see the other digits. So is life. But moreover, why is it the case? Why was it solvable? Why wasn't it, S6? Well, the reason it wasn't X6 is because of the symmetry. Let's look at this table. If we believe that there is an explanation for this symmetry along the columns, this suggests that there's an involution. These 36 solutions should be in bijection with those 36. Those 270 should be in bijection with these. There should be an involution somehow. Right? If there's an involution, well, there's an involution on this 6, right? So this says that there is some kind of map from these 6 solutions to itself. There's an extra symmetry. And whenever you have extra symmetry, the Galois group becomes small. For example, we saw a picture of a cubic surface earlier. If you take a cubic surface, then you learn in geometry that there are 27 lines on every cubic surface. Naively, we might think, Emil, that the 27 lines, that the Galois group is S27, right? That the Galois group permutes the 27 lines. That is not the case. There's a very high degree of symmetry on this Galois group. The 27 lines have so much structure and so much symmetry that the Galois group is tiny. It's a so-called group E6, Weil group of E6. Okay? And the same happens here. So we have an extra structure that drops the Galois group. Okay, so let me state a theorem. In fact, two theorems that explain the symmetry along the column. So we stated this as a conjecture in the first paper, and then Dreisma and Rodriguez solved the conjecture subsequently. Here's the first statement. The first statement is that symmetry holds. So if m is less than n, in either the general or the symmetric matrix case, the ML degree for rank R and for rank m minus r plus 1 coincide. Okay? So that was what we saw on the table. The second statement is a more refined statement that gives a more precise explanation. So suppose I have my data matrix U. So I have my soccer hair matrix. I'm going to form a new matrix of the same size, omega U, the dualizing matrix, whose entries are rational numbers. And what I'm going to do is I'm going to take Uij, so in row and I in column J, I'm going to take Uij times the row sum times the column sum divided by the cube of the sample size. Okay. If you paid attention, you notice that this is the Hadamard product of the rank 1 solution, the Bologist solution, times the full rank solution, the Parrot tautological solution. The theorem says the following. Suppose I have strictly positive data. Every possible outcome occurs. No pregnant males. Then there is a bijection between the complex critical points of the likelihood function on the rank R model. So I can label the complex critical points P1, P2 up to PS. And on the other model, on the co-rank R minus 1 model, I can label them Q1, Q2 up to QS, same S, such that the following holds. P1 times Q1, Hadamard product, is equal to P2 times Q2, Hadamard product, and they're all equal to omega U. Okay? What does this mean? Well, this means that all the structure is preserved. This means if I know QS, I can compute PS by Hadamard division, right? This is a matrix with positive rational number entries. So if Benjamin gives me this matrix, I can divide every entry, right? And I can calculate that matrix. Now, if this has real entries, that has real entries. If this has positive entries, that has positive entries, and so on, right? So there is a perfect involution, and this explains the Galois discussion earlier. Let me say this differently. Suppose one of these problems is hard, right? In fact, that happens. So it happens generally in these algebraic calculations that the high rank calculations tend to be a little harder than the low rank. So it's quite hard to find these 2,341 critical points, and it's easier to find those. Well, to solve the problem here from a statistical point of view, so to find the maximum, solve the maximum likelihood problem here, it's equivalent to solve the minimum likelihood problem there. So I compute the critical points there, I Hadamard divide, I get the critical points there. Right? So immediate implication. So the order reverses, right? So you can see additively, right? This number plus this number equals this number plus that number equals this. So, you know, it's perfect, right? So in each column, the first and the last equals the second plus the fifth equals the third plus the fourth. And that's why I could solve in radicals. Okay, there was a question? Yes.
Why do you know that the intermediate values are local minimizer, maximizer, not just critical points?
No, I don't know that in general. So in this example, they were. So in general, there will be critical points. So maybe again, for the students, right? So all I'm doing is I'm listing the critical points, and I'm keeping the ones whose coordinates are real and positive. Those are the ones I'm mostly interested in. Then I apply the second derivative test. Right? So in the second derivative test, what I do is I look at the Hessian of the objective function, and I restrict the Hessian to the tangent space. And then if the restricted Hessian is negative definite, then I have a local maximum. If the restricted Hessian is positive definite, I have a local minimum, or anything in between. And all of these things can happen. It was just in that example, they happen to be maximum minimum. I see. I don't know, actually. That's a very good question. I don't know. Yes, so I don't know the answer. So the question was, okay, suppose, in general, is it the case that the indices are complementary? And I don't know the answer. A good question. We didn't ask that. Very good question.
An elementary reason why this is true?
Well, the paper is it's a matrix, it's like 8-page argument of matrix calculation. So the proof is elementary, but it's not obvious.
But is it really about this problem that's on, or is it about complementary varieties?
We don't know. So that's an open problem. So at some point, Jose thought, he believed that every variety has a dual in this sense. That doesn't seem to be the case. But it seems to be a more general phenomenon. So for example, at this point, we don't know whether this is true for tensor rank. So we don't know yet. It's hard to get to do these calculations. We don't know. Ultimately, I hope that there will be a topological explanation. So I hope in the future, at some point, one can really explain this by topology. At this point, we don't know. So at the moment, as a theorem, it's for arbitrary matrices, symmetric matrices, and skew-symmetric matrices. There's also a version of this. Okay, let me shift gears, and let me talk about numerical algebraic geometry. So the reason we were so confident in these conjectures, and the reason we were able to fill the table much beyond what we could earlier do with Gröbner bases, is the advent of numerical algebraic geometry, and in Bertini in particular. So computing in algebraic geometry in the last, say, 2 decades was mainly predicated on Gröbner-based algorithms. So symbolic computing tools that have Gröbner bases as the engine were mostly used for computing in algebraic geometry. And platforms such as Macaulay, Singular, and so on and so on. In recent years, numerical methods have been developed. In particular, there's one software called Bertini, based on homotopy continuation for finding all complex solutions to a system of polynomial equations, and much, much more. So many of the computations that algebraic geometers are interested in, like decomposing varieties, computing cohomology, and so on, can be done numerically in Bertini. Okay? So this software was developed by Bates, Hauenstein, Somesi, and Wampler, and they have a new book that's coming out. And this is also, we have this new Computer Science Institute. There's one program where this will also appear. So let me say a word how this goes. So you have a system of equations that depends on some parameter. So maybe this parameter is my data space, U. Well, so then for some particular value of U, maybe I can find the solution. So maybe if some initial value nu naught, I can find the ML degree many solutions. But then I want to find the solution for some other value. Well, the idea is that I track numerically, right, from this point to that point, following the vector field given by the equations. Right? And, well, you might think that this leads into problems, right? You might think that you see this kind of behavior, 2 solutions coming together, or that some solutions die. This doesn't happen, right? Because the discriminant down here, the discriminant where this happens, is a hypersurface. It has codimension 1. But remember, this is the complex numbers. Over the complex numbers, every hypersurface has a connected complement. You can always walk around every hypersurface, right? So over the complex numbers, if you change your data in complex space, this will never happen. What will happen is at the very end, two might come together, this kind of thing can happen, but you're not going to lose any paths. Okay? So that's how homotopy methods work. Specifically, in our case of likelihood problems, this works quite well for the following reason. Suppose I'm interested in a model of a particular kind. So maybe I'm interested in 4x5 matrices of rank 3, let's say. I'm going to pre-process this problem once. Okay? I'm going to pick my own 4x5 matrix once. It's going to be some complex matrix that's very, very well conditioned. Okay? I'm going to solve. I'm going to find all 891 critical points. I'm going to let the program run for a long time, and I find them to very high accuracy. I'm going to save them on a file. Okay? Now Dimitri comes along. He gives me his table. He says, can you solve the likelihood problem for my table using this model? Well, I'm going to pull out these from my file. Right? I'm going to track from my data to his data. These paths I'm going to give to separate processes. This is entirely parallelizable, and in no time at all, I have solved his problem. Right? So here, I'm transforming the critical points of U0 to the critical points of U, and this amounts to changing the data. So here are some timings that are in our paper. So this was computed by Hauenstein on 160 processors. So it takes about an hour to solve the first instance for this model. Every subsequent run takes 20 seconds. Okay, question?
How do you interpolate between the two matrices?
Pardon me?
How do you interpolate between the two matrices?
This is the complex, so this is data space. So this is the space of a 4x. So I'm choosing an arc over the complex numbers, right? So I'm going, I forgot, lambda. So the naive thing would be to do this. So this doesn't work, right? So you cannot pick your real, so if you pick a real lambda between 0 and 1, it doesn't work. But you take lambda from 0 to 1 along a curve, a suitably general arc in the complex plane, then it works. So for lambda equals 0, that's the one we can solve. For lambda equals 1 is the one we want to solve. But we drive the lambda through the complex plane from 0 to 1, but not along the real axis. That's clear?
Because you exit the space you're trying to stay on.
Yeah, well, I want to stay away from the discriminant. So I want to stay away from two solutions coming together. Okay, so that's a little advertisement for numerical algebraic geometry. Okay, I only have one more slide and one more slide of references, and I have 9 minutes left. Any of the young people, any of the non-experts have a question? Okay, then let me make a remark. So there's another way to think about this problem, right? So I have my model. So here is my distributions, and here is my variety of low-rank matrices, and here are my data. So my data is a point here. Right? What am I trying to do? I'm trying to find somehow a close point on this variety that's close to my data. However, in the maximum likelihood scenario, I do not take the Euclidean distance. I'm going to take something called the Kullback-Leibler divergence. So in this context, what the statisticians often use to measure the distance between two probability distributions, it's a non-commutative. It's a non-symmetric distance called the Kullback-Leibler distance. So what we're doing is we're minimizing the Kullback-Leibler distance from our given matrix to all matrices of low rank. But maybe you could also say, well, why don't we just take the Euclidean distance, right? Why don't we use the Euclidean distance? And this is actually quite exciting. So Reka Thomas and I, with some collaborators, we're currently working on a related notion called the ED degree. So there's an ML degree for maximum likelihood. There's an ED degree for Euclidean distance. So you can ask the same for Euclidean distance. And it's a parallel story that's actually very, very interesting, and in some sense, many similarities and some differences. But if you think that Euclidean distance is more interesting than the maximum likelihood paradigm, talk to Reka or me. Last remark, kind coming back to the statistical situation. And this actually applies to both ML and ED. Well, that's all very nice, right? We have this value theorem. I showed you how to do this. The only problem is I solved the wrong problem. From an applied point of view, I did not solve the right problem. From the applied point of view, the right problem is not the low rank model, but the actual mixture model. So let me give you the technical definition. The mixture model is the set of m by n matrices giving distributions that factor as follows. A times lambda times B, where A is a non-negative skinny matrix whose rows sum to 1. Lambda is an R by R diagonal matrix, again, non-negative entries summing to 1. And beta is a lying down skinny matrix, non-negative, whose columns sum to 1. Okay. Such matrices P are distributions of non-negative rank at most R. So the difference between what we did and what most applied people really want is the difference between rank of a non-negative matrix and non-negative rank of a non-negative matrix. So in most applied problems, the notion of non-negative rank appears to be more interesting. Why is that the case in our context? Well, if you take the soccer table, the soccer hair table, and you break it as a sum of the male table and the female table, you want the female and the male table to have non-negative entries, right? If you have your 3 by 3 table of rank 2, if you write it as a sum of 2 tables, you want those to have rank 1. So that's why you want non-negative rank. So let me give you the smallest example where they differ, since we have enough time. So for example, let's look at the following matrix: 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1. Okay? And let's scale it by 8 to make it a distribution. So this matrix is a non-negative matrix of rank 3, right? Because the vector 1, minus 1, 1, minus 1 is in the kernel. That's a rank 3 matrix. But the non-negative rank is 4. But non-negative rank 4, right? If you decompose this as a 4 by 3 matrix times a 3 by 4 matrix, no matter how you do it, you're going to pick up some negative entries. Okay? So this will be explained. I think there's a lot of work. I think one of the Friday afternoon lectures is on non-negative rank and semi-definite rank. So this is an active area of research, the difference between rank and non-negative. Now, if the rank is very small, they agree, right? So if the rank is 2 at most, then the mixture model is the same as the low rank model, and they always equal up to the risky closure. But if R is 3 or more, then they differ. And that's just a fact of life. So the picture, talk to me if you're interested in convex polynomials. So here's the picture. So again, here's all the distributions. And let me draw my variety of low rank matrices like this. So these are the variety of matrices of low rank. But the ones of low non-negative rank, well, they are Zariski dense, but they're not everything, right? They will be sort of like this, right? They might share part of the boundary, but they'll be like this. So this white part is MR, matrices of low rank, and here is mix R, matrices of low non-negative rank. That's it. Right? There's another way to think about this yellow region. It's the image of a polytope under this polynomial map, right? So there's a parameter polytope. So these are the matrices A, these are the matrices lambda, and these are the matrices B. So those are the statistical model, the statistical parameters. So the matrix A, well, it tells us for soccer watching, it tells us for soccer watching what we think is the distribution of among males and females, how much soccer they watch. This matrix B is the distribution among males and females, how much hair they have. Right? Those are the parameters. And then this is the lambda. That's just in the population how many males and females there are. Right? So if we multiply them together, if we have this trilinear map, so we have this polytope, right? So we have this convex polytope mapping into our simplex, and the yellow semi-algebraic set is that image. That's the one we really want to optimize the likelihood function. That's what statisticians really want. Now, how do statisticians actually do that? So what's very common in statistics is to use a local method called EM, the expectation maximization algorithm. And that's a local method that works in parameter space rather than image space. And it will find a local maximum in the yellow region. Okay? Now, independent of EM, let's just think about the critical points of the likelihood function on the rank R model. Well, the following thing, you know, there might be many critical points, maybe 191, right? So there are 191 points here, 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 here. Okay? So there are 191 critical points. Now maybe the one we like best is here, then we win, right? Then that will be the optimal solution, and with some luck, the EM algorithm will also find it. In practice, however, that almost never happens. So in practice, the yellow volume is very small compared to the white volume, and usually, you know, Bertini lands here. Okay? And the true optimum over the non-negative rank locus will be on the boundary, and it will not be critical for the likelihood function on the determinantal group. So what we really need to do is we need to look at the boundary. We need to look at these codimension 1 strata that describe the boundary of the non-negative locus. I'm almost done. And we need to find the ML degree, or ED degree. I think we're done. And we need to find the ML degree or ED degree of this. So this is the real problem, okay, to understand the boundaries of the non-negative rank locus. We wrap up. So this is just a bunch of references. So in addition to the papers I mentioned, so there's the book by Bates and Company and Bertini. There's a paper by Feinberg and collaborators that describe exactly this class of latent class models in statistical language. Algebraists are often worried because the numerical methods, these path tracking methods, you might make numerical errors. You might lose the path. And already 20 years ago, Steve Smale proposed a method for addressing that, the so-called alpha method, alpha theory. And this was recently implemented by Hauenstein and Sottile, the alpha certification. So this is a way of making very, very careful steps along the homotopy that guarantee, that provably do the right thing, and that slows down the computation. We ran this on some of our instances, and it slowed it down by a factor of about 100. So we were about factor of 100 slower, but you were certified now that everything was correct. That's the old paper with Hoshten, where we did the first calculations. June He and myself, we have a sort of a longish article on likelihood geometry in general, which I think should be a good introduction. We were particularly interested for a while. I was a bit obsessed with the 4x4 tables. So I was particularly interested in 4x4 tables. Because the rows and columns were called ACGT, right? So we had some instances of where the states were the nucleotides in this book with Pachter, and there was a particular instance I really wanted to solve, and I gave a course, Nachdiplomsvorlesung, in 2005 in Zurich, and I challenged the students to solve a particular instance. So what I had done, it was a 4x4 matrix of rank 2, and at that time I didn't know about the 191, right? So I ran the EM algorithm 100,000 times, and there were 12 local maxima I knew about. Okay? But I didn't know how to prove it. So I offered 100 Swiss francs for anybody who could actually prove that the observed maximum was the actual maximum. Nobody did it at the time, but then these guys, Chinese graduate student, actually solved it, and I had to pay 100 Swiss francs, but I was very happy because this really propelled the progress, and we now understand the situation better. Thanks for your attention.
Since you don't seem to like the real numbers, what is the difference?
My relation, so I mean, correct it, right? So it's a little bit like world peace. It's a great idea. So real numbers are a very good idea.
Okay. The question is, what is the difference between the non-negative rank for real numbers and other fields?
Yes. So for questions like this, the real algebraic numbers are fine, right? So statements about non-negative rank, can be made expressed over the integers with the usual arithmetic and Boolean operations. So any statement over the real numbers will be the same as over the real algebraic numbers.
Like rationals, because you can send them.
Well, I like rationals and finite extent. I like numbers I can send by email.
Okay.
Very good.
Rationals and reals.
And certainly finite extensions of the rationals are fine.
But you don't know whether it is the same for rationals and reals.
Reka, what's the story? I think is the non-negative rank.
It's unknown.
I think it's known that it's not even like rank.
Do we have an example?
I mean, even like rank.
Oh yeah, sure. The pentagon, right? So isn't that the? Yeah. So the answer is no. So there are matrices. There are 5 by 5 matrices where the non-negative rank is different over the rational numbers and over the real algebraic numbers.
This published.
Yeah. So this matrix, if you think about this, this is the so-called slack matrix of a regular square.
Yeah.
If you do the slack matrix of a regular pentagon, then you really need the, I guess, the golden mean, right? The golden, right, to write this down. So Reka knows Reka and Pablo know everything about this.
Okay.
A stupid question of a non-expert, an old one. You have this formula that the Hadamard product of two solutions of the same rank is constant across the ranks. So yes.
In this one?
So, but this can also help you to not to go beyond this symmetry line between R and M minus R, right? So suppose you have R prime for one pair, R prime, M minus R prime. You know one factor, and then take another pair, R, M minus R, you get the missing other second factor. So you can even
Maybe I don't completely understand.
you can vary across the rank beyond the symmetry. This is an equation where four factors are involved.
For matrices.
Four factor matrices.
Yeah.
If you know 3, you get the fourth.
But 1 is trivial to compute.
3 you have to compute.
I mean, 1 is trivial to compute. P1, Q1 is trivial to compute, so you don't need 3.
In fact, you just
Maybe,
exactly
maybe
just
the idea
do
was
nothing.
that you know some entries here and some other entries there.
Okay,
something.
but you can
Maybe.
even right.
Yeah, I mean, you can use this in I guess you could use this in different ways. You could maybe use it as a primal dual method, searching for both at the same time. I should maybe say one more thing. So earlier I talked about duality in convexity, optimization, and projective algebraic geometry. They're the same duality. And that's an additive theory. That has to do with planes being tangent. Under this additive duality, rank R matrices are dual to co-rank R matrices. This is fundamentally different. This is a multiplicative theory. So in this multiplicative setting, rank R matrices are dual to co-rank R minus 1 matrices. And we really don't completely understand it yet. But this is really different, from convex and optimization duality. But as you say, we can really use this in various ways. We could imagine setting up some primal dual EM algorithm or something.
Questions, comments? Let's thank Bernd once again.